All right, fresh off those power notes, I'm going to try these 43 through 46, see how that goes. My memory is that these are pretty easy problems. Let's see. So 43, a force of 5 newtons. Oh, you know what we forgot? Dang it. Well, let's see. Probably you're going to watch this at some point. So go back and add to your notes. What are the units for power? Well, let's see. If power is energy over time, then if it's the slope of that, that would be joules per second. If it's force times velocity, that must also be equal to newtons times meters per second. But in this case, just like with what's a joule anyway, joules are newtons times meters, force times a distance. So force times the distance divided by time, that's the same as that. But we have a special name for this. This is a watt. And we abbreviate that capital W. Now, if you're thinking to yourself, wait a second, that is going to be super confusing because capital W, that's work, right? And now capital W also means watts. That's unit too. Well, I think in practice it's not going to be confusing because it should be very clear from whatever context you're working in whether you're talking about some variable quantity work or whether it's a unit of measurement. So I haven't. Initially, that seems like what a bad choice, but it works out. It works out just fine. All right. So what do we got here? 5 Newton force acts on a 15 kilogram body. It's initially at rest. Compute the work done by the force in the first, second, and third seconds, and then the instantaneous power due to the force at the end of the third second. Okay, so force, I think I need to know here, this is just the net force. It's the only force acting on the object. So let's see, force is equal to mass times acceleration, since that's the only force there is. So it looks like my A is a third of a meter per second squared. So let's see where we are. See at time 0. And then at time 1, where are we at? So here, since I have a constant acceleration, my delta x is going to be 1/2 times a t squared plus vit, but the initial velocity is 0. So it's just this. So after 1 second, the position is going to be at 1/6 of a meter. And then at time 2, we're going to be at position 2/3 of a meter. And then at position time 3, rather, that's going to be 9. That's going to be 3/2. So I think I need to figure out the way that they're phrasing that. I hope it's not confusing. Like the work done during the first second, that's like this displacement, and then this, and then this. This is during the first second, during the second second, and during the third second. So I need to figure out what these distances are here. This is going to be 1/6, because from 0 to 1/6. This is from 1/6 to 2/3. So let's see, that's 4, that's a half. Right, fractions. You know you love fractions, right? And then 3/2 minus 2/3. Let's see, that's, if we change things to sixths, this is 9/6 minus 4, so this is 5/6. So for A, B, and C, for part A, we want to know the work done during the first second. So work is equal to force times distance. So in this case, that's going to be equal to the force times that distance that it moves there. So that's 5/6 of a joule. Work is energy. And then for B, the same force times a half, 5/2 of a joule. And then for C, 5/6, 25/6, 4 and change. That all looks good. Book wrote those in decimal form for you, so you can have them that way if you want. And then how about the instantaneous power due to the force at the end of the third second? Well, our choices for instantaneous power would be either the derivative of energy with respect to time or force times velocity. So I know what the force is, 5 newtons, so if I just knew how fast it was going there, that would be the easy way. So I'm going to choose to do it that way. So let's see how fast my velocity at 3 seconds is equal to 1/3 of meter per second times time plus the initial velocity, which is just 0. So the velocity at time 3 is 1, which should be obvious. If you start from rest and you're ticking up 1/3 of a meter per second every second that goes by, you're going to be at 1. So that's 5 times 1, which is 5 watts. And that's it. Skier is pulled by a tow rope up a frictionless ski slope that makes an angle of 12 degrees with the horizontal. The rope moves parallel to the slope with a constant speed of 1 meter per second. The force of the rope does 900 joules of work on the skier as the skier moves a distance of 8 meters up the incline. So, what is it, 12 degrees? And skier is going to start here, holding onto the tow rope, and they're going to go 8 meters, and the work done is the work done by the rope, by that force, does 900 joules of work. Putting that that's work done by the rope is 900 joules, and it's constant velocity here of 1 meter per second. All right, what do we want to know? If the rope moved with a constant speed of 2 meters per second, how much work would the force of the rope do on the skier as the skier moved a distance of 8 meters up the incline? Well, this goes back to our notes. The example, where did it go? Like all these people's pushing these boxes. If we have different velocities here, but the same distance, then if those velocities are constant, then that forces are equal. So if it moves through the same distance, there's no change in the amount of work being done because it's still constant velocity, so it's still the same force. So if the rope moved with a constant speed of 2 meters per second, how much work would it do? It would still be the same 900 joules. I don't really need to do any math to figure that out. For part B, at what rate is the force of the rope doing work on the skier when the rope moves with a speed of 1 and 2? Well, let's see. I would need to figure out what that force is first. So if I know how much work is done, then work is, they told me it was 900 joules. Force times the distance is 8. So the force is, what is that, 112.5 or something? 900 divided by 8. Yeah, so that's about 113 newtons. So for part B, the power when the velocity is equal to 1 is equal to force times velocity. Sorry, that's watts. And the power when the velocity is 2 is equal to about 225 watts. It's force times velocity. Right? All right. Not too bad, not too bad. Oh, there we go. Burning through another piece of paper. This one. This is a good one. This is a good piece of paper because not only is it mostly blank, but it actually has the answers to 45 and 46 right there. How did that happen? So 45, a 100 kilogram block is pulled at a constant speed of 5 meters per second. And across a horizontal floor by an applied force of 122 newtons directed 37 degrees above the horizontal. So okay. What is the rate at which the force does work on the block? In other words, power, right? What is the rate at which work is done? That is what power is. So I think if I can figure out, so this is the little dot product thing, or the nod that if the velocity is this way and the force is this way, then we have to do force times velocity times the cosine of the angle between them. Or in other words, it's just the part of the force that's going like in the quote-unquote right direction. All right, so you can set that up however you want, but at the end of the day, it's going to be 122 times the velocity times the cosine of 37. And that's it. 122 times 5 times the cosine of 37. About 490, I'm guessing. They're going to keep 2 sig figs. Is that, yep, 490 watts. And 40, so I guess I lied when I said that we're not going to use this. I couldn't think of any problems. There it is, right there. 46, the loaded cab of an elevator has a mass of 3,000 kilograms. And moves 210 meters up the shaft. In 23 seconds. At a constant speed, so that speed would be just distance divided by time. 210 over 23 is about 9.1 meters per second. And at what average rate does the force from the cable do work on the cab? Well, if it's moving up at a constant speed, then that tension force from the cable, if it's going at a constant speed, must be equal to this. So the at what average rate does the force do work? So this is actually, yeah, we're looking for the rate of we are looking for power here. So that is going to be very easy for us to do if we just do this. So this cable is exerting that much force, and the velocity is 9.1 meters per second. So that's it. That's about 27,000 watts. And just in case you don't believe me about these things, there they are. That's what we got. All right, so moral of that story is power problems are pretty easy. When they come up, it's not going to be something that we do a ton with. You know, you will make many more force diagrams in your physics journey with me than you will do problems that require you to calculate power. But that's the thing we need to know how to do. And when it comes up, it's pretty dang easy.